Hello, everyone. This is Bill Bittner from IBM. Our next speaker today is Mike Friesenegger from SUSE, and he'll be covering 4 use cases when using SUSE products with IBM Z and LinuxONE. So with that, I'll turn it over to you, Mike.
All right. Thank you, Bill. Welcome, everyone. Thanks for everyone to stay on the last session of the day, especially to the people over in Europe and other parts of the world where you're staying up late to listen to me talk. So I promise I'll finish on time. So let me go ahead and move over to the next slide. And if you haven't seen me before, this is what I look like. I am part of the global IBM Alliance team at SUSE. I'm a solution architect. So that basically means that I get to work with just about every group in IBM, whether it be IBM Systems, the Z and LinuxONE groups, the Power groups, IBM Cloud, IBM TSS, GTS, and all of that. I'm based in Colorado, and I'm missing seeing all of you and chatting with all of you, which I would have loved to do, but events didn't allow that to happen. From an agenda perspective, there are 4 use cases I'd like to talk about, and you can see these on the screen, but let me take a moment and just run through those. First of all, building repeatable images for LPAR, ZVM, and KVM. Second is assessing impact of a security vulnerability. Third, make mission-critical applications more resilient to unexpected failures. And fourth, minimize reboots when running mission-critical applications. Now, these 4 items are from the perspective of if you're utilizing or taking advantage or want to take advantage of certain SUSE products. And I know this is a VM workshop, but I have the ability and I have access to SLES running in an LPAR. I have SLES running ZVM, and I also have KVM running on SLES in the LPAR. So I've taken the opportunity to build demonstrations for each of these 4 use cases, and kind of mix and match a little bit. It's primarily going to be KVM based, but also ZVM based demonstrations. So you'll be able to see a little bit of both and see SUSE and SUSE products running in all of these scenarios. Before I get into the first of the 4 use cases, just want to go over a couple of slides, kind of give a background of what SUSE and IBM Z and LinuxONE have been doing for the last 20 plus years. There's a lot going on in this chart. I'm not going to spend a lot of time on it. You'll have the PDF. I already sent the PDF in of this presentation, so you're welcome to look at it and ask me any questions or make comments or whatever. Just to give a little bit of a background of what SUSE is up to these days, most of you are familiar with SUSE for the bottom box or near the bottom. That's SUSE Linux Enterprise Server. But SUSE has been growing, the reach of our company, growing the number of employees we have, as well as growing the things that we can offer our customers. And so everything from advancing what we can do from a Linux operating perspective and doing more to bring and make enterprise open source available to our customers, not just in enterprise Linux, but also doing that for Linux systems management, around virtual machines and containers, doing things within the public cloud, and even what I consider above the stack, where we're talking about container management, container orchestration, and application delivery, as you can see at the top of this diagram. But for today, the focus of this presentation is primarily on things that you can do with SUSE Linux Enterprise Server. We'll talk about virtual machines and containers a little bit, and Linux systems management. Those green areas that I've highlighted are the focus of today's presentation. All right, let's focus on the first use case, and that's building repeatable images for LPAR, ZVM, and KVM. So there is an image building tool within SLES called Kiwi. Actually, it's an open source project available on GitHub, also known as Kiwi NG. NG stands for next generation, so you're probably thinking there must be an older version. If you are thinking that, you are thinking correctly. Kiwi NG, or next generation, is version 9, completely rewritten in Python. Kiwi, the older version, the traditional Kiwi, is version 7, and that was written, I believe, in Perl. If you're taking advantage of Kiwi, that's included in SUSE Linux Enterprise Server, in SUSE Linux Enterprise Server 15 Service Pack 1, it's in the Development Tools module. So as long as you've subscribed your SLES 15 SP1 system, you can go ahead and easily add the Development Tools module, which is included in the subscription, and then install the Kiwi packages. The cool thing about Kiwi is you can use it to build not only SLES images, but you can build other Linux distributions that I've listed here, whether it be RHEL or Ubuntu, as well as OpenSUSE, CentOS, Debian, and a number of other ones. In the GitHub project, we include image descriptions for a number of Linux distributions, and we also give examples of the different image types, the image formats, whether it be virtual disks or raw disk images or bootable ISO, or even building a container. Kiwi can build a container for you. If you're utilizing Kiwi in SLES, there's some additional packages that are included. We call them our JUICE, or Just Enough Operating System template package, that is available, but it's really only available for x86. It's included in the S390X media. You can install it, but when you crack it open and look at it, you'll see that the definition basically is x86 64. Well, I said that's not cool, so I'm working on the IBM Global Alliance. I've been working on creating the JUICE templates for S390X and also for IBM Power-based systems. You can click on this link here, and you'll be able to get access to the JUICE template for S390X with documentation how to use it, which I've expanded on more than what you get just out of the SLES media. So I talked about the use case of being able to create a reproducible image. You know, we probably all work with images, gold master images and things like that. Many of us probably have already done this many times, where we manually install and then we use some kind of tool to back up the image in ZVM or KVM if you're using KVM, but there's a very manual process. You have to have a long list of steps you have to follow, and if you forget a step, you've got to start over, or you've got to adapt, or things like that. What's really cool about utilizing Kiwi is that you describe the image in XML. Part of that description tells what the image type is, whether it's going to be PXE bootable image, a Vagrant, a container, a QEM disk image, a raw disk image, what the partition layout is going to be, what type of file system you're going to have, what packages are going to be installed, what users you're going to add, things like that. You can also add optional scripts that'll be run in the chroot environment for additional flexibility. You can also drop in customized like tarballs or additional files into a root directory structure. And what's really cool about this, and what you'll see when you click on that here link on the previous slide, is that you'll be going to my personal GitHub repository, and I'm using Git for version control, and as you follow the document and follow the directions, you can jump to different tags within Git and get different versions of image descriptions that I've created. Over on the right-hand side, you can see a little bit of what the XML image description, this is not the full thing, but you can see it even includes the ability to support profiles. So I have profiles for like KVM or KVM unpatched, and you'll see why I'm doing KVM unpatched here in just a moment in the next use case. I have an OpenStack-based description for being able to deploy to an OpenStack environment, and I also have a raw disk image that you can deploy to a raw ECKD or FCP. Not all of these profiles are available in the documentation yet. I'm still working out some things, but you'll see updates happening to my personal Git as I go along. All right, so let me jump to the video. And if you've never seen Kiwi before, let me go ahead and take a moment to show you Kiwi in action. So we're starting with the Kiwi Builder. And the first thing we're going to do is look at the definition directory. And the definition directory here is for a SLES 15 or SLE 15 Enterprise juice that I've adapted from the original template in SLES, but I've adapted it to S390X. You can see that it's got the .kiwi file, that's the XML file. It's got the script files, config.sh and images.sh. It is a root directory, and I could be pointing to these things. In the root directory, then I've actually have a bootloader file and etc sysconfig. All right, so let's go ahead and continue the video, and let's build a Kiwi image. And very quickly, it went by quickly, but I'm building actually a KVM image in this example. And it's juice, just an operating system. So we're dealing with a relatively small image file. The build process happens very quickly. Now I have used the magic of editing videos to speed up what you see the runtime, but it takes, I think, about 4 minutes in real time. Here it's happening a little bit faster because I've sped it up just to conserve on time. And very quickly here, it'll finish up, and it's created the KVM disk image. In this case, it's a QCOW2 disk image, but there's also a raw disk image, so I can look at it both ways. There's a little script that I created that's part of my documentation that makes sure the image will boot properly. It rebuilds the initRD. There are some things that I need to work with the engineering on and the upstream community to make sure that this works properly. So I copied the image file over to the KVM host, and now I'm going ahead and start it up. And this happens to be a first boot based configuration. So it's going to boot up and it's going to ask some questions, and you can see I'm going through pretty quickly on what it's asking for. But pretty quick here, we will be at a login prompt. And I'll log in as root and just make sure that I can type the IP command and make sure that I've got an IP address. And you can see it is running on S390X. This happens to be a KVM virtual machine. Like I said, I'm working on the ZVM. I have to go through a few extra things that I don't feel comfortable making, telling everybody that you have to do this. So that's why I'm going to work with engineering to get that fixed before I provide information how to build an image that can be deployed to an ECKD disk or to an FCP-based device in ZVM or on an LPAR. And there we go. End of the video. Pretty quick. So I'll take a moment and Yeah, the link is not clickable in WebEx, absolutely. Like I said, when the presentation is posted, download the PDF and you'll be able to link to it. If you want it sooner, feel free to reach out to me. You got my contact information. Hopefully you made note of that before. All right, let's move to the second use case. And this is assessing the impact of a security vulnerability. Just because we're running on Z or LinuxONE doesn't mean that we are not vulnerable to security vulnerabilities, especially, anything that, well, everything's done by humans, but the Linux kernel with millions of lines of code, Linux in general, it needs patches over time. So how can you assess the impact of a Linux kernel vulnerability? Let's talk about that. So first of all, there is a product by SUSE called SUSE Manager. Everything that SUSE does is from open source. We make it enterprise ready. We deliver it as a product to customers, but everything we do, we also contribute back to the open source community. In this case, the open source community is called Spacewalk. And it is the genesis, or it is the baseline for what we do for SUSE Manager. We contribute back to Spacewalk, but we've actually had to fork the project to Uyuni because some of our submissions upstream weren't being accepted by the owners of the project. But what we basically allow customers to do with SUSE Manager is help in optimizing operations. And instead of having to go and individually touch individual systems, and when we're dealing with ZVM or KVM on Z, or containers for that matter on the platform, you're dealing in thousands, possibly tens of thousands of systems that you might need to go off and touch. If you had to go off and touch each system individually, generates a lot of human cost, a lot of painstaking work on the keyboard, maybe some errors and things like that. Being able to do that from a centralized console, web-based administration, not only does it allow you to reduce the costs of operation, but it helps reduce the complexity of managing the systems and maintaining the systems that you're in control of. And we do everything from provisioning to package management to patch management to configuration management, everything that you see in the list over here. One of the areas that I think shows off very nicely with SUSE Manager is around compliance. And when we talk about compliance, well, let me go off to the next slide. But if you have never seen SUSE Manager before, well, you get a demonstration here in just a moment. But if you're interested in trying it out, you can get an evaluation from SUSE.com, and you can click on the link, and you can actually, it takes you to the documentation of how to install SUSE Manager on IBM Z VM. So from a compliance perspective, there's many different things you can do, and just like the graphic shows, you've got a camera there. It's if you've got a video doorbell type of security system at your house, you're able to see things that are happening. Well, SUSE Manager helps you in doing those same kind of things for a number of things, whether it be validating your security settings or verifying patches or identifying remediating vulnerabilities. Also being able to check around security compliance. But the one that I really want to focus on as part of the demonstration is a CVE, or a common vulnerability and exposure. Many of us are part of much larger organizations. You may have a security group within your organization. They might be very distributed focused, and so they come frantically to you and say, Linux has a vulnerability, the Linux kernel has a vulnerability, and you need to tell me how many of your Linux systems that are running on Z are impacted by it, and we need to figure out what's going on. That's the genesis behind the demonstration that I'm going to switch to right now. All right, so we're going to start with SUSE Manager, and we're going to go over to the systems that I have registered. Now, this is a very small SUSE Manager. I literally have only 2 systems, but it did detect the IBM Z system that I'm running on, just through normal detection processes. But basically, I've got a 15 Service Pack 1 patch system and a completely unpatched system. And I actually used Kiwi to build these images and boot them up and all that kind of stuff. So you can see very quickly that the patch system, because I did this yesterday in preparing this demonstration, the patch system has no patches needed, but the unpatched system has 274 patches, and it's got the the little red exclamation point. So now let's go off and your security group has come over to you and said, we've got this CVE that is a problem. We think it's a problem for our Linux systems. We need to know, what systems are impacted. Well, if you're familiar with CVEs, they start with the CVE and then the year and then dash and then a number. I just happened to choose 0543 as an example, and I'm going to go ahead and audit my servers, and as you can see, the patch system has no action required. The Z environment itself, no action required. Well, it's not even affected in this case. And then the unpatched system, the patch is available, and you can see the patch. I'm going to highlight it here in just a moment, and you could click on that link, and we'll get to it a different way here in just a moment, or I could install the patch on this system. Now, what's really cool is these are both virtual machines running on Z, but SUSE Manager can manage Linux distributions running on multiple architectures, not just Z. It happens to be the SUSE Manager server here is running on Z. The virtual machines are running on Z. But if I had a power box, or I had distributed-based systems, Intel-based systems, if I had not only SLES systems, but if I had RHEL systems and Ubuntu systems, I could go off and be able to register the system and do some things with CVE audit. But for now, we're just focusing on SLES. Now we're going to switch gears quickly, and I'm going to show you if you had to do this manually. This is one example, but if you had to touch multiple systems, you'd have to probably go through this multiple times. And if you don't remember the command, you're going to have to spend a little bit of time looking for it, scrolling up and down, doing -- help. As you can see, I'm trying different things. Then I eventually remember, oh yeah, I go back to my notes and I remember that I've got a list patches command, and I can add a -- CVE parameter, and I can put in the CVE number that was given to me by my security team, and lo and behold, I see that the system is vulnerable. The problem is I have to go touch each and every one of the systems to be able to do this, or I have to write a script to be able to do this. Whereas with SUSE Manager, you type in the CVE number, you hit the audit the systems, and if you wanted to get that security person out of your hair really quick, you could actually export the report to CSV, get them, send it to them in email. They can go off and talk to their security folks or discuss what's the next step, while you can kind of take a breath and do a little bit of advanced searching to figure out, what is this CVE all about? So let's go ahead and do that. Let's look at the CVE. Let's plug in the information that they provided, and let's do a search. And as I scroll down, I am going to find, there's that number again, that advisory from SUSE. There's the CVE number that was given before. When I click on it, I go directly to the CVE database. And as I start reading this thing, they're sending me on a wild goose chase. This doesn't apply to the Z systems at all. This only applies to Intel-based processors. I can pick up the phone and tell them, hey guys, you're sending me on a wild goose chase. You need to update your scanning system so that it's more reliable and can tell the difference between your distributed systems and your Z system Linux instances. All right, let's see. I'm going to take a moment and look at. I don't think there are any questions from that section that I can see. Oh, okay. Yep, I see somebody's mentioning that I manage both the S390X and x86-64 SUSE from your SUSE Manager running a ZVM. Awesome, thank you. I'm looking at these comments from my phone, so all I see is the your initials, not your full name, whoever J is, so thank you. All right, let's continue on to the third use case. So making mission critical applications more resilient to unexpected failures. When I started working with Z systems, especially when I came to SUSE back in 2001, I had the opportunity to go to Poughkeepsie and learn a lot about the hardware and learn a lot about the capabilities of the system. There's massive amount of redundancy, as we all know, in the hardware. And typically, it's not going to be a hardware-related issue, although occasionally it can be. But you still have mission-critical applications, and you can fill in whatever application is mission critical to you. I'll give you a list of some of them here in just a minute that I think are mission critical. But basically, you've got this mission critical application, and for some reason, something happens that causes it to fail. At this point, who knows? The potential reasons for a failure could be hardware. Maybe not. 30 to 50 year mean time between failure. Maybe not, but maybe so. Actually, a card may go out that causes slow performance on your ECKD DASD devices or something like that. You could have an external factors or the list goes on and on. The one I think of most of the time is human error. Actually, my old manager from many years ago, he said it's the nut behind the keyboard that's going to do something stupid and cause that mission critical application to go down. And I've got a great example of when I was in France working and helping out on deploying something on AIX. This is many years ago, before I was at SUSE. I was looking at the AIX system here in the States, and I was remoted into that system, and I was typing commands, and I typed the shutdown command, but I wasn't paying attention to which window. The nut behind the keyboard shut down the ERP system here in the States. My manager picks up the phone and calls me the next morning, and well, I won't say what he said to me, but it was basically, next time you do that, you're going to be fired. It would have been great at the time if I had implemented something like an HA cluster, where I could have that mission critical application running on a node, and if that node happens to fail, the HA cluster is actually able to determine that node has failed or the mission critical application needs to be brought up on another node within the cluster. In this case, you see it's a 2-node cluster. We can do up to 32 nodes. You can mix and match. You could have one node being an LPAR. You could have another node being ZVM guest. You could have another node being KVM on ZGuest. And those mission critical applications that can be managed by SUSE Linux Enterprise High Availability Extension are everything from databases, whether it be off-the-shelf databases, Oracle, DB2, Sybase, open source databases, MariaDB, Postgres, Redis, message bus like IBM WebSphere MQ or RabbitMQ or other message bus systems, SAP components. The SAP HANA is big these days. It doesn't run on the Z system, but I'm still aware of a number of customers using SAP NetWeaver. For infrastructure services, we're talking about DNS and DHCP, email servers, web servers, NFS servers. For cloud services, we're talking cloud service providers like AWS. For storage, DRBD and iSCSI. Any Linux service or daemon that includes System 5 init services as well as Systemd services. And you can write your own custom resource agents for in-house applications that you would like to make highly available. So when Node 1 happens to fail, when you're using SUSE Linux Enterprise High Availability Extension, you can keep your mission critical application available. So let's go ahead and switch to the demonstration. As you can see, I have two windows here. The window on the bottom is my mission critical application. Really, it's not so mission critical. It's a web server that tells me where it's running. In this case, it happens to be on HA Node 1. And the top window is the web interface that allows you to interact and manage the HA infrastructure provided by SUSE Linux Enterprise HA. So I'm going to refresh the web browser, make sure that it's still showing on HA Node 1. As you can see in the Hawk window, HA Node 1 is the location where the group is running, and in that group is the Apache web server as well as a virtual IP address. Moving over to the nodes, you see there's two nodes, HA Node 1 and HA Node 2. Now let's take a look at some of the configuration information. I won't go through all of the configuration details, but let's just take a look at a couple of things: the group, the resource agent for the Apache web server, and the virtual IP address. And then I have a constraint, a location constraint, that actually has the group want to always run on HA Node 1 when HA Node 1 is available. So now let's go back to the status window, and let's take HA Node 1 and put it in standby mode. That way it actually is acting like it's coming down. That will force the mission critical application to be moved automatically over to HA Node 2, and you can see that just happened in the web browser when I refreshed it. Now if I go back to the resources, you'll see that the group is now running on HA Node 2. If I go back to the nodes and take Node 1 out of standby, bring it back online, the location constraint will force the mission critical application to move back over to Node 1. Let's switch to the fourth and final use case, which is minimize reboots when running mission critical applications. In the third use case, we focused on keeping the mission critical application up. If the node happened to fail or the application became unresponsive, SUSE Linux Enterprise High Availability would automatically kick in and do something to make sure that the mission critical application was available. It would either restart the application or move it over to another node within the HA cluster. In this use case, we're focusing more on patching and applying specifically kernel patches, which require a reboot of the system for the kernel patch to take effect. You can see in this diagram, in this picture, a 10-month period of time where there's a large number of critical vulnerability exceptions that require a kernel reboot. Now this is the old way of doing things, and you can continue to do that. But let me show you something that SUSE is coming out with here very shortly. SUSE will be releasing SUSE Linux Enterprise Live Patching for IBM Z and LinuxONE in the June-July timeframe. It'll be available for /12 SP4, /12 SP5, and the upcoming /15 SP2. The great thing about SUSE Linux Enterprise Live Patching is you can apply those kernel patches, not need to reboot, but also not impact the performance of your application, not interrupt your application while it's running. SUSE provides fixes for kernel bugs based on a scoring system. The scoring system is called CVSS, Critical Vulnerability Scoring System. The latest version of that scoring system is version 3. If a particular bug scores 7 or higher on the CVSS v3 scale, then SUSE is going to create a live patch for it. SUSE also is looking at issues that affect data integrity and system stability. In either of those cases, if we find a kernel issue that is affected or could affect you in either of these areas, then we will provide a live patch as well. In the demonstration that I'll be showing here in just a few moments, we're going to be showing off interacting with live patching via the command line, but that's not the only way you can do this. You can also use tools like SUSE Manager, which I showed off in use case 2, to apply live patches and deploy live patches to many systems versus doing one system at a time. Understanding live patching is pretty easy to do, even though it is a pretty complex thing that's going on inside of the Linux kernel. Basically, what's happening is a detour is being created around the old function, which has a vulnerability in it, to a new function that has been inserted that takes care of what the function needs to do without the vulnerability. As applications make calls to the function, they're being redirected to the new function by this ftrace functionality in newer Linux kernels. Kgraft, SUSE's implementation of live patching for the Linux kernel, takes advantage of ftrace to do all of the things that I spoke about before, causing no interruption to your application, no performance impact to your application. So let's go ahead and switch to the demonstration so you can see live patching in action. So I'm going to install the live patching product, and as you can see, I'm utilizing the SUSE connect command, and I've registered it. Now let's go ahead and actually install the pattern, and the pattern will contain the packages that make up the live patching product. Okay, now that live patching is installed, we're going to use the kgr command to interact with the live patching environment. Kgr status shows the live patching environment is ready. We're looking to see if there's any patches, which there are no patches right now. So let's go ahead and look at the updates that are available. Specifically, are there any kernel updates available? No. So we're running the latest kernel version. Now let's look at the kgraph patches that are available, and we see that 122_23 is the latest. Let's get some more information about that kgraph patch, and you can see I'm highlighting the git revision number here. Kind of remember that number because that'll be important after we apply this live patch to the system. Let's look at the current running kernel version. As you can see, it's 122.23, and if you look in the lower right hand corner, you'll see the hash, which is A098DD9. We'll look at that after we apply the live patch because that'll look slightly different. So let's go ahead and install the live patch. And you can see the live patch is being added to the system. The initRD is being rebuilt just in case the system needs to be rebooted. And now you can see when we do kgr and look for patches, the patch has been applied. This is actually the initial kgraph patch that's available for this case, it's /12sp5. And if you look at the hash now in the lower right hand corner, you'll see that a /lp- and then the hash number for the live patch has been added. So now that's how you're able to determine what live patch is applied to the system. So with that, I'd like to thank you for your time. Have a great day.